Brook, Canada. Professor Kourtis is well known for his work on the theory of strong correlated quantum systems. He's an expert in the theoretical modeling of quantum materials and has developed several algorithms for simulation of quantum computing and for combinatorial problems of decision, optimization, and counting. I now invite Professor Kourtis to deliver his talk. 50 minutes are for the presentation and 10 minutes for questions and discussion. Over to you, Professor Kourtis. Thank you.
Thank you very much for the kind introduction. And also, I would like to thank the organizers for putting together this event, which is really great, and also for inviting me to give this presentation. So let me start by sharing my screen. There we go. So in today's presentation, I will talk to you about recent work that we have been doing in my group on quantum simulation of various complex systems. In particular, I will talk about how we developed some theory and use the theory that we developed to model a entanglement phase transition on a quantum simulator, and also to characterize this transition using spin glass theory. Okay, so this is the title of my talk, and I should say right off the bat that this is work that I've done with my student Jeremy Cote, and we have already one publication already out, came out a couple of weeks ago on Physical Review Letters. And I will also be showing, apart from the theory, I will be showing some experimental results that are as of now unpublished, but we expect to post them on the archive pretty soon. Okay, so here's an outline of what I will be talking to you about today. I will start with a motivating example for what I will discuss, because in fact, the question I will be asking is very, very fundamental. And it has to do simply with measuring part of a quantum state and asking what entanglement is left after measuring part of the state. Then what I will do is introduce the ensemble of states that we have introduced in our work, and in particular show how they are related to a classical spin model whose ground space in a certain parameter regime is that of a spin glass. And next, what I will do is I will show you how this particular model is amenable to implementation on quantum circuits. Okay, and then I will introduce and describe the quantum circuits that we use to build these states. Then I will show how precisely because of this mapping to the spin glass model, the entanglement and its properties actually follow from classical spin glass theory. And this allows us to derive exact results for how the entanglement should behave. And also it gives us very useful tools for how to actually measure entanglement, which is a highly non-trivial task in general. And then I will show you actually how we go about implementing these things on quantum computers. And finally, I will just discuss everything that I will have shown you and conclude the talk. Okay, let's get started. So I want to start with a very basic thought experiment, okay, just to guide our intuition as to why what I will be showing you later on in the talk is new, okay? So suppose we have a quantum state that is made out of a tensor product of n bell pairs, capital N bell pairs. Okay, here I show this schematically on the left, where each oval represents a bell pair. Now, suppose that we want to cut this state in half. Cut this state in half in order to measure its entanglement entropy. And there are many ways we can split the system to two subsystems, A and B. But here we pick the one where we spread the bell pair across the bipartition of the system. And we do this for each bell pair in our state. So we get a schematic like what I show here on the left. Now, we know how to calculate the entanglement entropy of such a state. In fact, in this case, the entanglement entropy is really simple because basically each bell pair contributes one bit of entanglement, okay? So entanglement entropy is calculated in the usual way. We take the reduced density matrix of one of the two subsystems and then calculate its von Neumann entropy. Okay, so now let's take the state and ask what happens to the entanglement entropy as we measure the qubits of subsystem A one by one. Okay, so in the beginning, we have 0 measurements. I show this diagram here, which is the entanglement entropy S in units of log 2 as a function of the number of qubit measurements for the qubits in subsystem A. Since we have n bell pairs, we have up to n measurements, okay? So now, since each bell pair contributes 1 bit of entanglement, if I have n bell pairs, I have n bits of entanglement, okay? Because entanglement entropy is extensive. So this is what I show here. At 0, we have an entanglement of n log 2, okay? Now, so that's our first point on this diagram. How does the entanglement behave as we keep measuring qubits? Okay, let's start by measuring the first qubit in subsystem A. What will happen? This will collapse the bell pair. Okay, so now this bell pair ends up being two single qubit product states, and by result, what we have is a reduction of the entanglement entropy by 1 bit. Okay, and this is the second point I show here as an X on the diagram. So, okay, what happens when I measure the next qubit of subsystem A? Well, same thing as before, right? I will just reduce the entanglement by another bit. And actually, so on and so forth. Nothing else happens, right? If you keep measuring all the qubits of subsystem A, your entanglement entropy will keep reducing linearly in the number of qubits measured. Okay, so basically what I will get at the end, once I measure all of the qubits, is entanglement of 0, and all the points in between will lie on this line. Okay, so this is an intuitive picture of, you know, what might happen when you measure a simple state like this. Also, a similar thing happens when you measure an arbitrary state. Say you pick a state at random from a Hilbert space and you measure the qubits one by one until you have no qubits left. What you will get is an entanglement curve that looks kind of like this. It goes down monotonously and is continuous. The curve is continuous. Now, what I will be talking about in this talk is a situation where this is not what happens. In fact, what happens is very different, and I sketch it here. In fact, what happens is, as I measure progressively more and more qubits, there exists a point where the behavior of the entanglement entropy changes abruptly. Okay, in fact, as I will show below, this change, this non-analyticity of the entanglement entropy is due to critical behavior. Okay, and so we get entanglement criticality and a phase transition between two phases of entanglement. Okay, so we will see some non-analyticity of the entanglement entropy, and the questions are how to describe it and how to measure it. Okay, so this is the general phenomenon. I will show now an ensemble of quantum states that exhibit this behavior, and then I will show you how to measure this behavior. in experiment. Now, to describe our quantum states, I need to take a detour and go to classical spin models, and particularly spin models with disorder that are used to describe spin glass physics. Okay, so our states will be superpositions of ground states, classical ground states, to a classical spin model, which is called the p-spin model. And here we will take p equals 3, so it's this 3-spin model. How is this model defined? So we write a Hamiltonian, which is a function of a graph, a set of spins, and a set of couplings. The couplings, J, take values plus minus 1, and so do the spins. They are Ising spins. And G is a graph that determines the interactions. And so what you get graphically is a thing that looks like the cartoon I sketched in the top right, where you have a number of interactions, and each interaction has a subset of the spins participating in it. Okay, so here I have interaction 1 involving spins 1, 2, and 6, and so on. Okay, so if we write down the Hamiltonian, we can write it down like this, where we sum over all couplings or all interaction terms, which is this set Vj here. And so for each interaction, we have this term 1 minus J A is the index of the interaction, and then the 3 spins that participate in the interaction. In this case of interaction 1, we have spins 1, 2, and 6. Now, the ground states of this model, in the case where the couplings are unfrustrated, or rather, let me put it more simply, the lowest energy state possible for this model is 0 energy. Okay, in this you can see, because the product here of J with the spins can be at least, at most 1, okay? With a negative sign, 1 minus 1 will give us a 0, and everything else is an excited state. Okay, yeah, so the ground state is, ground states are states for which all of these terms yield 0, okay, a 0 energy. Now, this problem has a clever mapping to an even simpler problem. So the mapping is shown here. We take each coupling to be minus 1 to some Boolean variable, ya, and each spin, sigma I, to be minus 1 to some other Boolean variable, xi. And if you do this mapping, you can convince yourself that the solutions, the ground states rather, of the initial Hamiltonian right above are basically the solutions of this system of equations modulo 2, okay, where B is a Boolean matrix. In fact, this B matrix represents the graph G. It's basically its bi-adjacency matrix. This graph is bipartite because interactions only connect to spins and vice versa. And so this matrix B gives you which interactions are connected to which spins. Okay, so for example, we saw here in the diagram that interaction 1 is connected to spins 1, 2, and 6. And so here, the first row represents interaction 1, and the only non-zero elements are 1, 2, and 6. So you put a 1 into the elements that represent the spins that participate in your interaction, and you have 1 row per interaction. Okay, so this matrix is, its size is number of interactions by number of spins. And using this mapping, we can derive a number of interesting properties for the p-spin model, and this is all standard in the literature. For example, this review contains all the details, but basically, knowing just B, matrix B, we can easily and efficiently determine the number of ground states we can have, in the case that we do have ground states of 0 energy, which is given by simply 2 to the n minus rank of B. Why is this? So rank of B is the number of linearly independent rows and columns of of B. Now, if you do Gaussian elimination of the rows of B, you will get that you have rank B dependent rows, and the rest are independent. So n minus rank B are independent rows, and so it means that your y vectors for these positions are free. Okay, and so in this case, it means you have n minus rank B Boolean variables that are free. So you get 2 to the n minus rank B ground states. And so if you have the number of ground states, you can calculate something called the ground state entropy, which is equivalent to the entropy of this model at temperature 0, which is simply the logarithm of the number of ground states. Okay. Okay, so this is all classical. What does this have to do with what we want to do on our quantum circuits? Now, this is what I show in this slide, and it's a bit complicated, so it'd be best if you just follow me. So we start with a matrix B, which is what we had before. Now, each row of B can be expressed as a quantum circuit. Actually, each row of the equation, the system of equations Bx equals Y. Okay, so the first index Y, 1, we get a part of the circuit that looks like this. Okay, so we can store the parity of the first parity, the first interaction Y1 into a qubit. Okay, and then what we can do is couple this qubit with qubits representing the spins, and at the end store their parity. Okay, into Y1. Okay, and we do this only for the spins that participate in the interaction. Okay, so this is shown here. We use 2 gates. First, this one, the gate labeled 1 is basically a C0, where we transfer the parity of a qubit or toggle the parity of Y1 based on one of the spin qubits. Okay, and then a swap to bring it next to the next variable that we want to act, that we want to use to toggle the parity. Okay, so here, again, for the first row, we have we have the spin, the interaction storing the parity of spins 1, 2, and 6, and this is what I show here. We toggle the parity using spin 1, then again using spin 2, then we skip over 3 spins, and then we use the last one, and we end up with our parity here. Now, if you can do this for one row, you can do it for all rows, and this is what is shown here in this circuit. Okay, since in the beginning we don't want to bias any configuration of the spins over any other, we put all the spin qubits, rather the qubits that represent spins in the Hamiltonian, into the plus state, and then we put the interaction qubits into the 0 state, and then we do basically what I showed you here for each row of the matrix B. And then we end up with a state that has combinations of spin states, but entangled with their parities, okay, with the corresponding parity. So this is shown here in the language of quantum states. So we have, for each parity vector Y, we get Y in the output register, tensored with all the possible configurations X for which the equation holds. Okay, so how many such states are there? Well, there are ny, basically as many Y vectors are possible. And how many of those are possible? Well, these are rank B. Okay, these are the number of linearly independent rows of the matrix. So, okay, so this is what gives us our state at the output, and gives us the superposition of ground states of the p-spin Hamiltonian, but separated into parity segments. This is also similar to an LDPC code, to a classical LDPC code. Okay, so you can think of it as that, where Y's are the syndromes for each possible configuration of the bits. Okay. So what is cool about the state is that it is already written in the form of a Schmidt decomposition. So this state psi out, the way I've written it here, is already Schmidt decomposed. So it means that I can directly read off its entanglement entropy. And this is why we use these states. So if this is if you think of the Y part of the state as subsystem A and the X part as subsystem B, these are the Schmidt coefficients here. And so if we just plug in for the entanglement entropy, we will get basically ny log 2, and basically this is just the ground state entropy. Okay. So for this ensemble of states, we have a very simple expression and an exact correspondence between the entanglement entropy of the quantum state and the classical quantity, the classical ground state entropy of the spin glass. Okay, so why is this interesting? Now we can look at what happens when we measure the state. We will maintain an exact correspondence between the spin glass states and our quantum state, even as we measure. Okay, and in fact, what we can show is that as we measure progressively more interaction qubits, we will eventually transition into a spin glass phase where the entanglement entropy of our state is given by the ground state entropy of the spin glass phase. To understand this pictorially, I put this cartoon here that shows what happens as you progressively measure your Y qubits one by one. Okay. So in the beginning, when you have measured only one or a few of these qubits, the rest are pretty much free to take whatever value they want. Okay, so this is what's indicated here. On the x-axis, we have the number of parity qubits measured. Parities are the interactions. And these dots here, when they're gray, it represents that the parity measurement can come out either way. Okay. Now, in the beginning, when you have measured only a few of these parity qubits, the outcome for the next measurement is pretty much 50-50. Now, what happens in a spin glass is that after you have fixed a bunch of these parities, then after a certain critical fraction of parities fixed, then the next outcomes start to be correlated. Okay, and that's the hallmark of the transition to a spin glass phase. And so statistically, past the transition, your measurements will statistically depend on the outcome of previous measurements in our setup. Okay, and so the idea here is to detect this transition as a function of measurement. Okay. In other words, the way to understand this is, in the beginning, if you don't measure anything, you have a lot of freedom in choosing your parity configurations of your parity bits. Okay, and so it means because of this freedom, their state is uncorrelated. Whereas afterwards, after you've fixed a bunch of them, now you cannot choose the remaining ones as you wish. So you get correlations between one configuration and the other, and that is basically a spin glass phase. Okay, so what does this mean about entanglement? Okay, because remember, we're not talking just about like a classical Hamiltonian. We now embed the ground space of the Hamiltonian into a quantum state. Because of the correspondence of the entanglement to the entanglement entropy to ground state entropy of the spin glass, we can now calculate things and derive expectations exactly and compare them to numerics. Okay, so here basically entanglement is a bit like gives us something like an order parameter, or rather a susceptibility for the two phases. Okay, and so we can derive a so-called entanglement susceptibility, which is the derivative of the entanglement entropy, as a function of this fraction of interaction bits measured. Okay, that I denote this as this alpha. Capital A is the region of the interaction bits that we measure, and so size over the size of our state, sorry, is this fraction. Okay. So we can take this derivative. Okay. Now I have replaced here already the entanglement entropy with the spin glass, sorry, with the ground state entropy of the classical model. And so we can see what happens in numerics and how we approach the theoretical expectation. Okay. So here I plot this entanglement susceptibility again in units of log2 as a function of this parameter alpha, and show what happens to it. Okay, for various sizes of our state. N is the number of qubits. Okay, we can easily simulate these quantum states because they are basically stabilizer states. And so we have an efficient way to simulate very large systems. And what we see here is the typical behavior of a phase transition. We have a non-continuity that sharpens as we increase the system size and approaches the exact result in the thermodynamic limit, which is a dashed black line. You cannot really see it here, but it basically follows just the envelope of the lines. And not only this, but using this data, we can do a finite size collapse, and we find that that the data collapses to a universal form with a certain critical exponent, and this critical exponent agrees with what is in the literature for the critical exponent that describes a spin glass transition. And we can also derive an order parameter. In fact, we can use the order parameter of a spin glass, the spin glass order parameter, which is basically the overlap between two different ground states of the spin glass, and then squared and averaged overall possible pairs of spin glass states. Okay, this is like an Edwards-Anderson type order parameter. And so what we find is that this order parameter also describes well what is happening and captures the transition that we have for a quantum state. Okay, because here we do these calculations using our quantum states. Okay, so it is a spin glass order parameter, but we use the measurements that we take out, that in this case we simulate on a classical computer to evaluate this order parameter. And again, we find a sharpening as we increase the system size and approaching the expectation, the theoretical expectation. Okay, so everything matches. We have a theory that describes what happens to our quantum state. We evaluate numerically our quantum state and see that it follows and converges to the theoretical expectation, which is no surprise because our mapping is exact. And in fact, here I show you the exact correspondence between the entanglement entropy and the spin glass order parameter. Q is the sorted parameter. S is our entanglement entropy for the state whose part A has been already measured. Okay, A relates to this alpha fraction, and basically in the limit, these two expressions become the same. So we have an exact expression. Also, this means that any critical behavior of the order parameter, the spin-glass order parameter, directly translates to non-analyticities in the entanglement entropy. Okay, so this is the formula that proves this. And another thing that we can read off from this, perhaps not quite directly, is that the transition that we find between these two entanglement phases is a transition between two volume law phases. So you have two different volume laws, but you have a critical point that separates the two. Okay, so we have all the ingredients needed to actually try and verify our theoretical expectations in our derivation. Okay, so we can put our theory to the test, and since now we live in the era of quantum computers and quantum simulators, it means we have access to these machines and we can actually use them and do the experiments ourselves. So we take off our theorist hat, we put on the experimental hat, and now we see what we can do using devices that are accessible to us. So here I show you the results that we get for the order parameter on the systems of IBM, okay, the IBM Q quantum computers, and in particular we use these three devices that I showed here: Washington, Hanoi, and Brooklyn. And basically what I showed you here is what I was showing you in the previous slide as an expectation, as a theoretical expectation. Here it's actually the real deal. Okay, this is measured on the quantum computers. The points show results for different system sizes, and we go up to 48 qubits. We are able to entangle up to 48 qubits, meaning entangling 24 spin qubits corresponding to spins, and up to 24 interaction bits. And so what we find here is the dashed lines in this figure are the theoretical expectations calculated for these system size and taking into account basically all the experimental parameters. So what we see in this figure is that the order parameter as a function of alpha follows pretty closely our theoretical expectations. Basically, almost all the points are within an error bar of the theoretical expectation value. The reason for this is that we have done quite a bit of work to mitigate errors and to optimize gate counts in our experiments, but I will spare you the details. I can discuss these later if somebody is interested. And so now one more thing that we can do is we can try to do a finite size collapse of all the data that we've used, that we have gotten from the quantum computer. And this is what we do here. Of course, a finite size collapse of such small systems is always to be taken with a grain of salt. But nevertheless, we find a pretty convincing collapse for at least these small systems. And we find an exponent for the order parameter that agrees with the result for the order parameter that is expected, that can be calculated theoretically, okay? So this is a pretty nice verification of the existence of such a transition on a quantum simulator. And as far as I know, these are the biggest results. I mean, the results using the largest number of qubits to do this kind of experiment on actual quantum devices. Okay, so next thing I would like to do is discuss these results a bit, because there are several things that are non-trivial about them, and I would like to bring your attention to those. The first thing is that the theoretical mapping that we obtain in this case is exact. Okay, there's no approximation done. There's no limit, spurious limit taken. Really, what we model classically is what we measure in the experiment, modulo errors, quantum errors. Okay, errors due to coherence or to readout. Okay, but we basically model exactly, our theory models exactly and analytically what should happen on the quantum devices. Second point is that here I've shown you that we measure an order parameter, and in the slide right before I showed you that this order parameter is basically the entanglement entropy. Okay, and in the previous slide I also showed you how the two correspond to one another, even graphically. So this is also a non-trivial fact, because measuring entanglement is in general very tricky. In the general case, one would need to tomographically reproduce the quantum state in order to then measure the entanglement. And of course, this is highly inefficient. It requires an exponential number of measurements, etc. So here we have a setting where we can extract entanglement entropy and measure it readily on the quantum computers. Another remark is that you may have heard about entanglement phase transitions in a different context. And this is the context of monitored random quantum circuits. So this is a line of research that was started in 2019 by these two groups. What they showed there is that if you intersperse measurements in an otherwise perfectly unitary quantum circuit, you can eventually drive an entanglement phase transition using this rate of measurements, right? So if you increase the rate of measurements, you can drive a circuit that would otherwise produce a volume law state to produce instead an area law state. And there is a critical rate. There's a critical rate between the two behaviors. So our work is different in a few respects. First of all, for the physics that is shown in that context, you need to intersperse measurements, do a round of measurements, then you entangle again, then you measure again, then you entangle again, etc. So the setup is more complicated. Secondly, even though there exist theories that pertain to explain the behavior in these systems, all those theories are approximate, and they work in a limit that is different. That's different to the experimentally relevant limit. So there are theories of percolation in Potts model with infinite local dimensions, whereas in fact local dimensions of qubits are 2. Okay, they have a Hilbert space of size 2. And finally, another remark here is that other proposals are quite difficult to implement. In fact, it's unclear how one would go about measuring entanglement and its transition in the most general case of completely arbitrary quantum circuits. And even in simpler circuits, again, in the case of what other people study, it's not trivial to implement. So we have different physics in our case because we build a state and then we just measure. So the question we ask is very, very fundamental. It's the thing that I showed you in the beginning. We build a state and then we start measuring qubits one by one, and we ask what can happen. Versus in these random circuit models, the questions are more complicated. And secondly, we in our case we have been able to make the measurement of entanglement efficient, and at the same time have an exact description of what's going on in terms of entanglement. One final remark that I would like to make is that the results that I'm showing here are valid for more general quantum states. So I showed in the cartoon of the circuit here, for example, that I started with an equal superposition of all spin states. Okay, and so this is a very particular state. It does simplify the derivations, and it allows us to get the analytical forms, and also simplifies the experimental part. But this is in no way, our results are in no way restricted to this initial state. So for example, in this figure here on the right, the blue curves show the uniform distribution of all spin states, which is the old plus state. Whereas the red curves, they show random or scrambled initial states. So basically we take a completely random state and we initialize our spin qubits with that state. Of course, in this case, we cannot do as large simulations, but we again get a sharpening, and we seem to follow the same theory for these states as well. Okay, with this, I can conclude so that there's enough time for discussions. We introduce a class of quantum states that exhibit an entanglement phase transition upon partial measurement. So it means that we start with a state that follows a certain law of entanglement, and as we keep measuring the qubits, we transition eventually to another law of entanglement. And there is a sharp critical point that separates the two phases where the entanglement entropy becomes non-analytic. Okay, and more than that, it behaves, it exhibits truly critical behavior, meaning critical exponents, etc. We have formulated a theory that describes exactly, in terms of spin glasses and their theory, both the transition, where it should occur, the location of the critical point, and the critical exponent relevant to the quantum state. And finally, we have also shown how the entire protocol of building the state, controllably reducing the entanglement with measurements, measuring a proxy to the entanglement entropy, and even verifying the criticality, how to do all of that on a quantum simulator. And on the theory side, again, we have shown that the results that we obtain are valid for more general quantum states than the ones shown here, and potentially even more general than what I discussed in this talk. So with this, I would like to thank Jeremy Cote, who is my student, who worked with me on this, did all the calculations and all the simulations on the quantum computer, and also acknowledge the financial support that funds our work. With this, I will take your questions.
Thank you very much for a very interesting talk. And now it's open for questions. So participants, you can unmute yourself and ask him directly. There was something in the chat box. In the meantime, if you can just check, I think there was a question in the chat box.
Sure, yeah. Okay, first question I see is how is volume law and entanglement entropy, how are the two concepts related? In fact, the volume law of entanglement directly tells you what the entanglement entropy should do. So volume law means that for an ensemble of states, as you increase the size of your system, meaning say you have an n qubit state, you increase n, your entanglement should be extensive with respect to n. So it should be proportional to n. Okay, that's the volume law of entanglement. Okay, next question is there any correspondence between criticality and the area law? Yes, in fact, it could be. So, okay, here we showed an example where there is a criticality between two volume law phases of entanglement. It might be that one can cook up a similar transition between two area laws of entanglement that are distinct. And even more, what one can have is a transition between the two volume and area law. This is in fact what happens in the case of these these random quantum circuits, where the criticality is really you drive the transition from area to volume, rather from volume to area, as you increase the rate of measurement. So here in what I showed you, we didn't pursue this sort of transition from volume to area law, because not that, in fact, it is possible. There is a regime where we can cause it. It's just that the description is more complicated, and we have left it this for future work. But in principle, we should be able to cause a similar transition using just measurements, as I showed here. Okay, another question. There are some entanglement entropy. Okay, that entanglement entropy results, I guess, that have already been described in 1D systems. Could you please tell us about particularly 2D systems? Yeah, so 2D systems, the laws, the volume and area. So first of all, a volume law doesn't depend on the dimensionality of the system, right? So volume law is volume law in any dimension. Means your entanglement scales as the number of qubits. Now, area law in 2D systems is, area law in any dimension is an entanglement that scales with one dimension lower than the physical dimension of the system. So in 1D, your entanglement saturates to a constant. In 2D, area law scales as the side of your system. Okay, so in principle, you could have transitions that are specific to a dimensionality. Okay, so here, what I showed, because the system is a random graph, there is no natural dimension. It's not embeddable in any finite dimensional space as you scale up. Okay, so the number of dimensions increases, in fact. So, but yeah, you could have instances where where you limit yourself to states that are defined on a physical manifold, and then you can ask similar questions. Okay. Can we also define entanglement phase transition in the quantum Ising model? I don't know. So here, these transitions are, well, okay, two things here. One thing to keep in mind that is important. So when we talk about phase transitions here, these are phase transitions as a function of measurement, okay? Entanglement phase transition can be as a function of anything, okay? So if you talk about the quantum Ising model, say the transverse field Ising model, where you say you tune the one of the parameters, say the transverse field, and you go from one phase to another. Sure, you might change your entanglement, going from one phase to another, or say from one phase to the critical point, but this is not as a function of measurement. Okay, so here, what we are talking about are transitions that can be caused just by measurement. So to simulate a similar setting using the quantum Ising model, what you would do is prepare a quantum evolution using the Ising model, and then ask how many measurements would you need to drive, say, your phase from one entanglement regime to another. Okay, and this, as far as I know, I think there are some results, but the setting was not the same as what I was showing here. But that has to be the setting. Okay, it means you have a dynamical system, you have a unitary evolution, and then you measure either at the end, or you intersperse your evolution with measurements, and then you ask what happens to the entanglement.
Are there any more questions, comments?
I see one in the chat.
One more, yes.
Does volume law entanglement entropy, is it applicable for mixed quantum states? Oh boy, yeah. Mixed states are, the situation for mixed states is more complicated. is more complicated because for mixed states, there is no single useful definition of entanglement as in the entanglement entropy, right? The bipartite entanglement entropy that we use for pure quantum states, which is everything that I did in this talk, ceases to be a good characterization of entanglement for mixed states. Because it also captures some of the classical correlations, unfortunately, for mixed states. So it's not pure entanglement that you get. If you just take the von Neumann entropy of the subsystem, you don't get only the quantum correlations. Now, one interesting question to ask is there another quantity, say the mutual information or some other probe of entanglement that would show a similar critical behavior? And I think that's an interesting question. I think there's space for studying that in the future. Other questions?
Yeah, I think there are no more questions. So we would like to thank you once again for a very nice talk. Thank you.
Thank you very much for having me.
Okay, we still have some time before the next talk. So what should we do? I'm asking the organizers. Should I don't know if Professor Matskin has joined or not. Yes. Yes. Okay. Okay. Sure. Sure. Yes, please. Okay. Yeah, we'll start in a minute because then we'll be on the correct time. Okay.